Okay, so what we then have is we can consider a couple of things. What happens when with certain values of k? I've stated that k is an integer. Notice what happens when k equals 0. So here, I'm looking at what happens when k equals 0 in here. So we have k there, and we have a k hidden in there as a result of it being a depiction of the multiplication or the number of times we rotate round a cyclical circular-esque structure found in both the sine and cosine functions for certain outputs, if that's one way of describing it. The idea then is if k equals 0, then z equals 1, because if k equals 0, this becomes cos 0, I sine 0, and we've seen what that produces. That produces our original situation as we wanted. That produces this lovely cos 0 plus I sine 0, which is exactly what we wanted, 1 for the fact that z cubed equals 1, which could be described as the base of this argument. Now, then that's perfect. I've stated here when k equals 1, we get a z2, that's a subscript 2, a new complex number that we can show on our Argand diagram along with z0. So therefore, here, what I'm calling the original z, I'm going to put a subscript 0. There's a very large subscript. I'm going to keep it there just for jokes. Now, in these circumstances, we've got z0 is equal to 1. That's this one here. This is our z0. And no, that's getting a bit too powerful for a subscript. I'm not going to produce a subscript. I'm just going to put z0 there. I'm saying that this here is z1. And what do I mean by that? Well, it means that if I plug in k equals 1 into these circumstances, you'd have, as I've described, as you can see here, you'd have cos 2 thirds pi plus I sine 2 thirds pi, which is minus a half plus I root 3 over 2. And you can see that produces this angle here, like so. And this also satisfies what we needed for z cubed equals 1. It is another value on another complex number that satisfies the circumstance of z cubed equaling 1. If you plug in these values, you'll end up with a minus a half plus I sine root 3 over 2, and it will satisfy our trigonometric circumstances. When k is 1, it is shifting you along to this new point here, which is the same point there. That's a bit elaborate. Let's move up here. Same point here when it is a output value of 0 for sine and an output value of 1 for cos, which is what we need. 0 for sine there. Output value of 0 for sine. So there's no lift. There is no imaginary part. There's an output value of cos. That is 1. So there is a value of 1 on the real axis. And so it satisfies an equal to 1. This is a representation of z cubed. So this also is a solution to the answer z cubed equals 1. Now let's also move on to k equals 2. You'll find that for k equals 2, we have a little bit of a problem. What happens is we end up with cos 4 thirds pi plus I sine 4 thirds pi. Recall that the arg, the angle we have been discussing with respect to complex numbers, which I can use a little paint brush here to illustrate this angle there. Very badly drawn on the paintbrush, but y'all know what I'm talking about. That angle is defined between minus pi and pi as a result of convention. It's not always minus pi and pi as well. It could be 0 to 2 pi in certain circumstances, depend on the field of mathematics or how you're using mathematics as a language in whatever field you're in. The idea is that therefore, this here, 4 thirds multiplied by pi, which is in these circumstances equivalent to 180 degrees, there's no way that will fit within this realm, so we cannot use k2. And I said, therefore, when k equals 2, we come into contact with a problem, and we will discuss how we deal with that problem next time. But for now, what we can note is we have found one solution, which is just the cos 0 plus I sine 0, which gives us z0, and that's for k equals 0. For k equals 1, we have found a new solution to z cubed equals 1, which is that there.